Hello everyone, welcome to the course on Emerging Domain Electronics Engineering. This is lecture 2 and in this lecture we will see the Zener diodes. So in Zener diode we will see how the Zener diode can be used as the voltage regulator, how the Zener diode we can see what are the breakdowns, what types of breakdown occurs in Zener diode, and also we will see what are the application areas of Zener diode. So first of all we will start with the definition of Zener diode. It is a heavily doped semiconductor device. Means this Zener diode, the doping level is quite high in comparison with the conventional P-N junction. So these are the specially designed diodes which generally operates in the reverse direction or in the reverse bias. So clear, Melvin Zener was the first person to describe the electrical properties of the Zener diode. So as I have already told you that a Zener diode operates just like a normal diode when it is a forward bias. Means under the forward bias condition, the Zener diode works in a similar fashion like a conventional P-N junction diode. So when in the reverse bias region, there is a small minority carrier current which is also referred as a leakage current which starts flowing through the Zener diode. But as this reverse voltage increases and it reaches a value which is called as Vz, will generally denoted this Vz as the Zener voltage. So it has been observed that the current starts flowing through the diode. As further we are increasing the value of voltage, the current will be reaching its maximum value. Further, if we are increasing the voltage in a conventional P-N junction diode, so the diode generally break down. But in a Zener diode, if we are further increasing the voltage, it will gain a saturated voltage Vz. So generally there are two type of breakdowns which generally occurs in the Zener diode or in a normal P-N junction diode. So first type of breakdown here is the avalanche breakdown, which generally occur at higher reverse voltages, whereas the Zener breakdown generally occurs at the lower reverse voltages. So we will see what is the phenomena behind the avalanche breakdown and the Zener breakdown. So first is the avalanche breakdown. So this avalanche breakdown occurs in both normal diode as well as in the Zener diode at a high reverse voltage. So what happened? What is the phenomena behind the avalanche breakdown? So when we are applying a reverse voltage, so basically we are increasing the velocity of the minority charge carriers. So as the minority charge carrier velocity increases, the associated kinetic energy also increases. Now when this kinetic energy increases, so this high amount of kinetic energy is responsible for the ejection of valence electrons, means the electrons which are available in the outermost shell. So due to this continuous collision, a large number of free electrons are generated. So as a result of these large number of electrons, we can say that the electric current in the diode rapidly increases. So this sudden increase in the current is mainly due to it may destroy the normal P-N junction diode. But as we will see in a Zener diode, these Zener diodes are operate at a high reverse voltage. And these Zener diode doesn't break down, they generally sustain these spikes which appears in the current. So avalanche breakdown generally occurs in the Zener diode at a voltage which is greater than 6 volts. We will see that the Zener diode is, this Zener breakdown basically occurs in the Zener diode which is below 6 volts, which is basically the difference also between the avalanche breakdown and the Zener breakdown. Next phenomena is the Zener breakdown. So as we have seen that both type of breakdown occurs in the reverse bias situation. So when we are again increasing the reverse bias voltage across the Zener diode, what happen is the depletion region will become narrow, and due to this narrow depletion region, the electric field will become too much intense. It will become very strong. Now this strong electric field is now responsible for the ejection of electrons, means the valence electron will be pulled out from the valence band. So the valence electron then gains the sufficient high energy from the strong electric field of the depletion region and they become free from the parent atom. So at the Zener breakdown region, a small increase in the voltage results in the rapid increase in the electric current. So as we are increasing the voltage further, so it has been observed that the current increases sharply. So here we have the characteristics of the Zener diode. So we can basically categorize the characteristics of Zener diode in two different regions. First is the under the forward bias region and next in the under the reverse bias region. So what happened, as we can see here, that under the forward bias region, the Zener diode is very similar. The characteristics are very similar with the conventional P-N junction diode. Means we have the cut-in voltage which may be 0.3 to 0.7 based on the germanium and the silicon. So the graph is quite similar. But here what we observe here is that as we are increasing the reverse voltage, so what happened? We have the minority carrier current. The minority carrier current which starts increasing. But as I was telling you that as we reaches the voltage which is called as Vz, so what happened at this Vz, the current start increasing in the opposite direction like this. So we have a maximum value of Zener current which can be denoted as Izm, and also we have a minimum value of Zener current which can be defined as Iz minimum. So here at this particular region, in this particular region we can say that the Zener diode is providing a constant voltage. So we can use the Zener diode as a voltage regulator. Means whenever the diode is operating in this particular region, the diode will be providing a constant voltage. That is the application of that is a major application of Zener diode. Now we will see what are the approximate or the equivalent circuits, how this Zener diode can be used in the application. So we are dividing the characteristics into three regions. First region which is the forward bias, second region where the voltage, applied voltage is less than Vz, but the voltage is between Vz and 0, and next is the C region where we are increasing the voltage, reverse voltage further beyond Vz. So here we can see that under the A situation here, under the forward bias condition, the diode can be represented by a battery of 0.7 volt. Means it's nothing but a similar kind, it's nothing but a similar to that of conventional P-N junction diode. But what we are observing between 0 to Vz voltage, the current is 0. We are approximating here that the minority carrier current is very small, and we are assuming this to be 0, and the diode can be replaced by the open circuit. So this is the B region. Next is C region, which is very important here, that the voltage reaches Vz, the diode here can be represented by a battery of Vz. The magnitude is Vz. So we can use the Zener diode under the forward bias condition and under the reverse bias condition. But generally the Zener diode is used in the reverse bias condition under this C region. So next we are going to see how we can utilize the Zener diode and what all are the possible cases regarding the regulator. So regulator circuits are basically the circuits which provide a constant voltage irrespective of the variation in the input voltage, or we can say irrespective of the variation in the load resistance. So on the basis of this we can consider here three different cases. First is the very easy case where the input and with the input voltage and RL is a load resistance, both are fixed. And this case we can consider this as an investigation case, that we need to check whether the circuit is working as a voltage regulator or not. We will see what are the conditions here. Second case where we are fixing input voltage, means the input voltage is fixed whereas the load is variable. Again we will check that under what circumstances, what is the possible range for the load resistance where the circuit is working as a regulator, means the circuit is providing a constant voltage to the load resistance. And the third case here is that we are fixing the load resistance and we are varying the input voltage. We will see what is the satisfactory range for the input voltage, so that the regulator will provide, the circuit will provide a regulated voltage to the load resistance RL. So first we will start with case 1, when input is fixed and RL is also fixed. So first we need to check, we need to analyze, we need to check that whether the diode is on or off. So for this we need to remove the diode here, and we are calculating the open circuit voltage. We are saying this as VOC. So how we can calculate the value of VOC? VOC can be obtained by applying the voltage divider rule. So VOC will be V input multiplied by the load resistance divided by series resistance plus load resistance. Let me tell you, this is a basic circuit for a regulator where we have a series resistance RS, or we can say R, the load resistance RL, we have the Zener diode, and we have the input voltage. So while applying this open circuit voltage, we will investigate whether this open circuit voltage of V is greater than Vz or less than Vz. So then only we will be able to say that the Zener diode is in on state or it is in off state. So if we observe here that if VOC is greater than or equal to, the marginal condition is equal to. So when the Zener diode voltage, when the open circuit voltage is equal to Vz, means we are at this particular moment, then what we can say, that the Zener diode is in on state. Here the diode is on. But when VOC is less than Vz, what we can say, that the Zener diode is off, and when the Zener diode is off, we can say that the diode is open. The diode can be represented by its open circuit equivalent. So we have both the conditions here, when input is greater than Vz and when VOC is less than Vz. Now we have the second step here is that substitute the appropriate equivalent circuit and solve the desired unknowns. What are the unknowns? The unknowns are the current, the load voltage, the current in the series resistance R, the voltage across the series resistance R, what is the maximum power dissipation through the Zener diode, which can be represented by PZM. PZ is a power in the Zener diode where capital M corresponding to the maximum value. So if we can see that if VOC is greater than Vz, diode is on, and we can say that if IR is a series current and IZ is a Zener current, so we can say that IL here is a load current. Now using KCL, what we can observe, that IR, incoming current, equals to outgoing current. So incoming is IR and outgoing current is IZ and IL. So we have an equation which is IZ equals to IR minus IL. This is very, very important equation, because this equation will be helpful in case number 2 and case number 3. Also, we can say that the power dissipation by the Zener diode is determined by Vz multiplied by Iz, means the Zener voltage multiplied by the Zener current. So this is these are the steps how we can analyze a regulator circuit under the first case. Now based on this first case, we will see a small numerical here. So for the Zener diode network, determine the load voltage, which is VL, the voltage which is VR across the series resistance R, Iz, which is a Zener current, and PZ, which is a power dissipation through the Zener diode. So first case, here we have the load resistance 1.2K, also the input Vi is 16 volt, means we can clearly see here that both input and RL are fixed. Means in this particular case we need to basically check whether this diode is working as a regulator or not. So how we can initiate this? First we will remove this Zener diode from here and we will calculate the open circuit voltage. So VOC here can be written as 16 multiplied by 1.2 divided by 1 plus 1.2. So here if we will calculate this value VOC, so this VOC will be definitely less than VZ. Here I have already calculated that VOC is 8.73. So once this VOC is less than VZ, then we can clearly say that diode is operating in the region B. So in the region B we can say that the current is 0 and diode will be open circuited. So what is the value of, from this characteristic curve also we can say that we are operating at this particular region, and at this particular region the current is 0. The current is 0. So VL, what is VL? VL is same as what we have calculated, which is 8.73. Now if we will apply KVL here, so VR, this voltage is VR, this voltage is VI, and this voltage is VL. So what we are calculating VR is, VR equals to VI minus VL. VI is 16 and VL is 8.73. So we can calculate here that the voltage drop across the series resistance is it is 7.23. Now as I was telling you that the Zener current is 0. Why the Zener current is 0? Because here it can be represented as open circuit, and we are already aware in our open circuit network the current is 0. So if the current is 0, then the power dissipation PZ will be VZ multiplied by IZ, that will also be 0. Means what, from this particular case what we can say that when the load resistance is 1.2 K, the circuit is not working as a voltage regulator. So we have increased the load resistance here, and we are considering the second case where the load resistance is 3 kilo ohm. So we are increasing from 1.2 K to 3 K. So let's see what happened under this particular situation. The diode will be on or off. So again we will calculate here that what is the open circuit voltage V. So again I am using the voltage divider. So 3 multiplied by 16 divided by 1 plus 3, the voltage will be 12 volt, which clearly indicate that 12 volt is greater than the Zener voltage, which was given 10. So when 12 volt is, when the open circuit voltage is greater than VZ, that Zener diode is on. The Zener diode is in on state, means it is operating in C region, and it can be represented by a battery of VZ volt, and this particular numerical it was given that VZ was 10 volt. So what happened? The load resistance will be equal to VZ, because in parallel branches the voltage will be equal. So VL equal to VZ equal to 10 volt. Now we are utilizing a similar kind of relationship here, that VI equals to VR plus VZ, or VZ equal to VL. So we can find out here that VR equals to 16 minus 10, which is around 6 volt. Now we are aware with this VL, so we can definitely calculate the load current. Load current can be obtained by VL by RL. So 10 volt divided by 3 ohm, the result will be around 3.33 milliampere. Now the current IR can be calculated as, if we will apply KVL in this particular loop, so we will be having 16 minus 10 divided by 1, which will be 6 milliamperes. Now we have IR, now we have IL, so we can definitely calculate what is the value of IZ here. IZ equals to IR minus IL, so we can calculate IZ equal to 2.67. So once we are calculating with the Zener current, then we can definitely calculate the power dissipation through the Zener diode. So PZ can be given as VZ multiplied by IZ, which is 26.7 milliwatt. Means for this particular situation, what we can say, that when the resistance increases from 1.2 kilo ohm to 3 kilo ohm, so the circuit is working as a regulator, but at 1.2K the circuit was not working as a regulator. That means if we have applied a load resistance having a very small value, so it will not be able to turn on the Zener diode. We have to increase the value of load resistance. So we have the second case where input is fixed but the load resistance is variable. So there has to be a specific range for the load resistance RL for which the Zener diode is in on state. Means this is the condition that when the Zener diode is in on state, then what is the value of RL? So as I was telling you in the previous question that too small load resistance means when the load resistance value is very small, it will not be able to turn on the Zener diode. So we have to sufficiently increase the value of load resistance. So how can we perform the analysis for this? The analysis is quite easy. To determine the minimum load resistance that will turn on the Zener diode, means this is the important condition, that what is the minimum value of load resistance to turn on the Zener diode, which is simply calculating. Simply what we are doing here, we will calculate the voltage across the Zener diode and will put this value equal to Vz, because we are saying that the Zener diode is in on state, and when the Zener diode is in on state, the open circuit voltage will be equal to Vz. So with the help of this voltage divider and by simplifying this, we have calculated the value of RL minimum. So RL minimum will be R multiplied by Vz divided by Vi minus Vz. So we have calculated the minimum load resistance. So once this load resistance is minimum, what we can say that the voltage is fixed. The voltage across the load resistance is fixed, but resistance is minimum. So what we can say that the current will be definitely maximum in the load, which can be obtained by IL maximum equals to Vz by RL minimum. Now we can clearly see here that we have the relationship that VR equals to Vi minus of Vz, this equation. Now since Vi is fixed, Vz is fixed, and also VR is fixed, so what we can say that the current which is IR in the series resistance, which will also be fixed, it will also be a constant value. So I have the equation here corresponding to the current Iz equals to IR minus IL. So what here we can say that if Iz, if the current IR is fixed, this is fixed, and if I am saying that the current in Zener diode is maximum, if the current in Zener diode is maximum, then naturally what we can say that the current in the load resistance will be minimum, because we have to obey this relationship. Also we can conclude here that the current will be maximum when the Zener diode current is minimum. So both the equations are true. So once we have calculated the IL minimum, the load current, the minimum value of load current, then we can calculate the maximum value of load resistance, which is RL maximum. So what are the steps here? First we will calculate the minimum load resistance, then we will calculate the value of series current IR, next we will be obtaining the value of RL maximum. So this is a procedure to basically calculate the case number 2, means when input is fixed but RL is variable. Now we have a small example here. In this particular example, it is given that instead Iz max we have Pz max. So either you are given with the Pz max, the power dissipation, maximum power dissipation in the Zener diode, or we are given with the Iz max. So we have 20 volt input and RL is unknown, and series resistance which is fixed, which is 220 ohms. So we can clearly see, we can clearly understood from the statement also, for the network determine the range of RL and IL. Means we have to calculate the range of RL and the range of load current. That will result in the voltage drop across the RL being maintained at 10 volt. Means the voltage drop across the RL will be fixed, which is 10 volts. So we have to find out the satisfactory range for the load resistance as well as the load current. So we'll start with the same here, that first we'll calculate the voltage V. So V equals to 20 multiplied by RL divided by R plus RL. So we don't need to learn any formula here. We are already aware that since this open circuit voltage, when it is equal to Vz, then we can say that what happened, we are having the minimum value of load resistance. We can clearly see that Vz is given, we are given with R also, resistance also. So we can obtain the minimum value for load resistance. Also, how we can utilize this Pz max? So Pz max we can write down equals to Vz multiplied by Iz. So with the help of this particular relationship, we can calculate the value of Iz max. So which we are going to utilize when we are calculating the maximum value of load resistance. So here we can clearly see that we have obtained the minimum value of load resistance, which is 220. Also we have utilized the relationship for Pz max, and we obtain here that the current, the maximum Zener current will be 40 milliampere. Means we cannot exceed, the current cannot exceed beyond 40 milliampere in a Zener diode. Now with the help of Iz max, I can calculate here what is the value of load current, what is the minimum value of load current. So that will be 45.45 milliampere minus of 40 milliampere. The value will be 5.45. And now we are utilizing this value to obtain the value of RL maximum. So RL maximum will be VL divided by IL minimum. So here we can see that the satisfactory range for RL will be 0.2202 to 1.83 kilo ohms. This is the range for RL. Also we can say that we have a range for IL, and the minimum value is 5.45 milliampere to maximum we can calculate. Maximum here we can calculate when this will be minimum. So when this will be minimum, it will be 0, and what we can say that the maximum value will be 45.45. Also we can calculate the minimum value using the relationship here. From this we can calculate IL max. Once IL max is known, so Iz minimum equals to IR minus of IL max. Naturally, because when the Zener current is minimum, so the load current will be maximum. So this is the second case. So we can say that when the load resistance is between this particular range 0.22 to 1.83 kilo ohm, the circuit is working as a regulator. But once we are having a value which is less than 0.22 and greater than 1.83, so what we can say that the circuit will not work as a regulator. So this is case number 2. Now we have case number 3 here. So in the case number 3, as I was telling you that we have the variable input voltage but RL is fixed. The load resistance is fixed but the input voltage is variable. So again we don't need to learn any formula here, we need to apply directly what is the voltage here, which is VL, when the Zener diode is in on state. This is the minimum condition. If you have to find out the range for input, then we have to assume here that the Zener diode has to be turned on. So by utilizing this, what I can write down, VOC equals to V input multiply by RL divided by R plus RL. So from this we can see that since RL is fixed, resistance is also fixed. So we can say if input is very small, if input voltage is very small, so it will not be able to turn on the Zener diode. So input has to be sufficient high so that the open circuit voltage will be equal to Vz. So we are obtaining the minimum value of input voltage by putting VOC value equal to Vz. So this is the final relationship what we derive here, that input voltage is RL plus R multiplied by Vz divided by RL. So this is a minimum range for input voltage. Now how can we obtain the maximum range for input voltage? So for this we are going to utilize IR. Here we have IL and here we have IZ. IR equals to IZ plus IL. Now if load resistance is fixed and we are saying that the voltage across the load resistance, this is also fixed and the value is Vz, so what we can say that the load current will definitely be fixed, it will also be a constant value. And if IZ is maximum, if the current in the Zener diode is maximum, then definitely the current in the series resistance R, means this current IR, will obtain a maximum value. Or else what we can say that, when the current in the Zener diode is minimum, then the current in the series resistance R will also be minimum. So we'll calculate the value of IR max, and with the help of this IR max we can calculate VI max. VI max equals to IR max multiplied by resistance plus Vz. So by this second formula here, by the help of KVL in this particular loop, we can calculate the value of maximum input voltage. So we have the example 3 here. Determine the range of values of input voltage that will maintain the Zener diode in the on state. Mean this is a primary condition. It should be given that the Zener diode is on state. Also, what is given in the numerical here, that the maximum Zener current is 60 milliampere. If this value is also not known, we are not able to find out what is the range for input. So we are going to basically calculate the satisfactory range for input voltage where the circuit is working as a voltage regulator. So how we can start? First, I'm going to start with the open circuit voltage or load voltage VL, which will be input multiplied by RL, which is 1.2 divided by 0.22 plus 1.2. We can clearly see here that this is given in ohm here, and here the value is given in kilo ohms. So we have to be very cautious about this, and when this value is equal to Vz, we can say that the input voltage is minimum. So with the help of this particular relationship, we can obtain the minimum value of input voltage. Now how can we calculate the maximum value of input voltage? So we can obtain the maximum value by first calculating the IR max. So IR max will be equals to IZ max plus IL. So what is the value of IL? As we are already aware, IL equals to VL divided by RL, and VL was 10 and VL was 20 here, sorry, and the load resistance is 1.2. So definitely with the help of this we can calculate the value of IL. Now the IL is known, and also in this particular question the IZM, which is the maximum Zener current, this is also known, which is 60 milliampere. That means we can obtain the maximum current, IR max. Once this IR max is known, we can use this value to obtain the maximum value of input, which can be given as R multiplied by IR max plus Vz. So by solving this particular relationship, we can say that we have a satisfactory range for input voltage where the circuit is working as the voltage regulator. So this case is also important. Case number 2 and case number 3 are quite important. Case number 1 is based on the investigation. So here we have seen all three possible cases associated with the Zener diode. So this is important here, case number 3 and case number 2. So these are the application areas of Zener diode. Now we'll see now, apart from this voltage regulator, what are the further applications. We have seen the Zener diode can be used as a voltage regulator. It can also be used as a over voltage protection. Means the regulator here, we can further say that the regulator can be obtained by using BJT also. BJT in series and BJT in shunt. Shunt means the parallel, and series we are already aware. So we can obtain a regulator, voltage regulator, with the help of Zener diode. Also we can obtain the voltage regulator using BJT as a series and as a in the series mode and in a shunt mode. Also we can use the Zener diode as a voltage overload protection. How we can utilize this Zener diode? As we are aware that in the reverse bias region here, when the reverse voltage is exceeding this Vz, then what happen? It will behave as a constant voltage. It will behave as a constant voltage. What happen? Only the current increases here, but the voltage will not increase. So it can be used as a over voltage protection. Also, the third application here is it can be used in the clipping circuits. So we are already aware what are clipping circuits. So clipping circuits are basically circuits where the input waveform is, some part of the input waveform is clipped off, either the positive half or the negative half. We have the it is also used in the shift voltage. Means if we want to shift the level of the voltage of the input waveform, then also we can use the Zener diode. So these are the major application. This voltage regulator is very important application area of Zener diode. And this over voltage protection, this is also used in the stabilizer circuits, where we need to protect the circuit. So these are the references here. Thank you.